The CH-47 Chinook justifies its place in the Army's helicopter inventory through its capability for multi-mission utilization. The Chinook's twin-engine, tandem-rotor design permits transportation of cargo, troops, and weapons during day, night, visual, or instrument conditions. The high payload capacity of the CH-47 further enhances its value as a tactical helicopter. Standardized cockpit procedures, as shown in this presentation, are an essential part of preparation for flight in the CH-47. Such procedures should be performed as specified by the checklist in the current TM-55-1520-227-10. For almost all steps, cockpit procedures are identical for both B and C model CH-47s. A C model was selected for the following demonstration of cockpit procedures. Cockpit procedures begin with a properly clothed pilot and co-pilot attaching seat belts and shoulder harnesses. Belts and harnesses should be checked for condition. The next step is adjustment of seats and pedals. Pilot and co-pilot seats are alike and are designed to provide 3 axes of travel. Seat tilt is controlled by a catch on the left side of the seat. Fore and aft travel is adjusted by a catch on the bottom right side. A handle on the right side controls up and down travel. Pedals are individually adjusted and held by a peg and hole system. Both pedals should always be in the same notch. Pilot and co-pilot utility lights are checked next. Each utility light has an on-off switch and intensity control. The intensity control on each utility light should be switched on in both white and red positions. Jettisonable release handles on both doors are examined next. Each door handle is fastened in a retainer with copper safety wire. Inspection of the upper shaft assembly leg projection into the upper latch plate area is required. The latch on the door bottom is similar to the top latch and should also be checked for security. Unlike the top latch, it is safetied with steel wire. The handle is on the outside for ready access in the event of an emergency. Pilot and co-pilot doors each have sliding windows, which may be opened or closed as conditions require. Operation of each handle and sliding assembly is necessary to ensure proper functioning. Before proceeding further, the co-pilot confirms an adequate spare lamp supply. The spare lamp box is mounted on top of the DC circuit breaker box to the left of the co-pilot's seat. Circuit breaker boxes are next on the checklist. Both AC and DC boxes must be checked to confirm all required circuit breakers in the in position. The DC box is located to the left of the co-pilot's seat, and the AC box is located on the right side of the pilot's seat. The fire extinguisher is mounted on the cockpit deck to the right of the pilot's seat. Make certain that the extinguisher floor mount is securely attached and that the inspection tag is current. Confirm that the extinguisher safety and seal are secure. The rear view mirror provides the pilot with a view of the cargo compartment. The mirror must be readily adjustable and securely mounted. The pilot must make certain that the outside air temperature gauge is securely mounted and that the glass surrounding the gauge is not cracked. If the gauge shows a believable temperature, it may be assumed that it is operating properly. Next, be certain that all circuit breakers on the overhead panel are set in the in position. For daylight flights, the following lighting switches must be placed in the off position. Pilot flight instrument light switch, anti-collision light switches, center section instrument light switch, dome light switches, and position light switch. The overhead panel light switch must be off, and the console light switch must also be off. The co-pilot searchlight control switch must be at retract. Co-pilot flight instrument light switch off. Emergency exit light switch in the arm position, and the formation light switch off. The APU start switch must be in the stop position. Make sure that the pilot searchlight control switch is in the retract position, that the floodlight toggle switches are in the off position, and that the floodlight rheostat is off. The engine anti-ice and pitot heat switches must be off. All three anti-ice, anti-fog switches must be in the off position. The number 2 engine start fuel switch must be closed, and the number 2 ignition switch must be off. The number 1 engine start fuel switch must also be closed, and the number 1 ignition switch must be off. Confirm the APU AGB ground switch in the normal position, red cover down. Be certain the utility hydraulic system switch is off, that the battery switch is in the off position, and that the number 1 and number 2 generator switches are in the off position. Hydraulic boost switches must be in the both position. The SAS switch must also be in the both position. Hoist master and hoist control switches must be confirmed in the off position. The cable cutter should be off. The cargo hook master switch should be off. The cargo hook emergency release switch must also be off. Place the right forward aux pump switch in the off position. The right main forward switch and the right main aft pump switch must be off. Confirm the right aft aux pump switch in the off position, then check to see that the cross-feed fuel valve switch is closed. Place the left aft aux position tank switch in the off position. The left main aft pump switch and the left main forward pump switch must be off. Confirm the left forward aux pump switch in the off position. The CH-47 has 2 emergency troop alarm boxes. The forward box is mounted on the left bulkhead above the avionic equipment shelves, while the aft box is in the cargo compartment on the left side of the fuselage at station 575. Each troop alarm box is equipped with a bell designed to alert passengers and crew with predetermined signals in the time of emergency. The bell should function when the troop alarm switch is placed in the on position. The jump lights are used to alert the flight engineer during airborne delivery operations or the troop commander during paratroop drop operations. Be certain the troop alert lights on the overhead panel and cargo compartment are illuminated. Return the switch to the off position. The heating controls are next on the checklist. The cabin temperature selector should be adjusted to whatever setting is required. The vent blower heater switch must be in the off position. The windshield wiper switch must also be in the off position. The next item on the list is the magnetic compass. It should have a correct heading and should be securely mounted. In addition, the magnetic compass should be filled with fluid and free of air bubbles. A current calibration card should be attached to it. The RMI card attached to the compass should also be current. The fire extinguisher agent switch mounted at the top of the instrument panel should be in the neutral position. Each of the control handles should be in the in position. Check the following instruments for static readings, slippage, and range markings. Engine instruments. transmission instruments, and hydraulic instruments. Check the pilot's engine torque gauge and rotor RPM gauge for static readings, slippage, and range markings. The co-pilot's engine torque gauge and rotor RPM gauge must also be checked. Examine pilot airspeed and vertical speed indicators, as well as co-pilot airspeed and vertical speed indicators. Place the transmission oil pressure selector switch in the aft position, and the transmission oil temperature selector switch in the scan position. The fuel quantity selector switch must be set to the total position. The VGI switch on the right side of the panel should be positioned to normal. The compass slaving switch should be in. The co-pilot's VGI switch should be set to normal, and the co-pilot compass slaving switch should be in. The altimeter on the co-pilot side should be set for field elevation. The pilot's altimeter should also be set. Set the co-pilot's clock to the correct time. Also set the pilot's clock. Cockpit air knobs on both sides of the instrument panel should be closed. The air control handles on the right side of the console should be adjusted according to weather requirements. The stick positioner should be adjusted so that the arrow points to 0. Next, check communications equipment and navigation radios. As radio configurations vary from aircraft to aircraft, individual communication components will not be referred to in this presentation. Be certain that the normal engine trim disable switch covers are down. The aft wheel swivel lock switch should be in the lock position. Check to be certain that the number 1 and number 2 engine condition levers are in the stop position. Place the emergency SAS release switch in the release position. Position the pitch stability augmentation switch to the auto sync position. Be certain that the speed trim function switch is set to auto. Then place the power steering switch in the off position. At this time, crew members should don flight helmets and gloves. The battery switch must now be turned to the on position, and a voice check made of the intercom system. Next, the flight engineer checks the operation of the fuel valve and crossfeed valve warning lights. Now the pilot confirms the master caution dimming switch in the required position and checks the master caution test switch. All caution capsules and the 2 master caution lights must be checked for proper illumination. Before proceeding with engine start procedures, make certain that your fire guard is posted, then perform the APU start sequence. Press to test the APU low oil pressure light, then place the APU start switch in the APU position. Check to be sure that the low oil pressure light is out and that the high EGT and overspeed warning lights are on. Place the APU AGB switch in the start position. Place the APU start switch in the start position. The switch must be held at start until the APU tachometer indicates 90%. When the APU tachometer reaches 98 to 106% RPM and the warning lights are out, the APU is running properly. When the number 2 hydraulic boost off caution light goes out, move the APU AGB switch to normal. Then check that the number 1 hydraulic boost caution light goes out. Turn number 1 and number 2 generator switches on. Note that the generator and rectifier caution light should be off. Then check flight control and utility hydraulic pressures. The flight control pressure range is between 2,500 and 3,200 psi. The utility pressure range is 2,500 to 3,400 psi. Next, set the flight controls. Cyclic and pedals should be in neutral, with the thrust control rod in the 3-degree detent position. Now check aft temperature, oil pressure, and temperature. The pressure reading should be 20 to 90 psi. The maximum temperature is 130 degrees. Place the pressure selector switch in scan. The transmission low oil pressure caution light comes on after the transmission pressure gauge goes below 20 psi. Before proceeding, select proper radio frequencies and turn communication and navigation radios on. Turn on the upper anti-collision light switch. The flight engineer should confirm operation of the light mounted near the aft rotor. Now turn on the lower anti-collision light switch. Operation of the underside beacon is confirmed by the flight engineer. Leave the lights on. The flight engineer may also assist in checking the landing searchlights. First, turn on the pilot's overhead searchlight control switch. Turn the searchlight filament switch on, then operate the position switch, extending the searchlight to assure proper operation. Turn the filament switch off and move the control switch to retract. The same procedure would be followed when checking the co-pilot's landing searchlight. The wheel parking brakes are checked next. Place your feet on the brake pedals and apply pressure to release the brakes. The parking brake handle should go in and the brake caution light should go out. To reset the brakes, continue to apply pressure to the brake pedals. Pull out the parking brake handle and release pressure on the brake pedals and handle. The caution light should come on. Reset the master caution light. Continue by checking the engine fire detection circuit. The detector test switch is located in the top center area of the instrument panel. There is one light on each end of the 2 T handles for a total of 4 lights. All lights should illuminate when the detector test switch is placed in the test position. They should all go off when the switch is released. Using the fuel quantity switch, check the following positions. Left aft aux, left forward aux, right forward aux, right aft aux, right main, and left main. A needle indicates fuel quantity and tanks selected. The total of these tanks will be continuously expressed on the digital readout on the fuel gauge. The stick positioner trim wheel should be checked next. Rotate the trim wheel full forward without holding onto the cyclic. The indicator should read approximately 1.5 inches forward. Then rotate the trim wheel full aft. The indicator should now read approximately 1.5 inches. The trim wheel should be returned to 0. Check the cyclic trim indicators located in the lower left center area of the instrument panel. Both needles should be fully retracted. Check the heater function switch in the overhead panel. It should be turned to the off position. If the heater has been operating, you must allow a heater purge period of 2 to 3 minutes before starting engines. Position of the rotors must be checked with the assistance of the flight engineer. Both forward and aft rotor systems should be clear of the fuselage. Check the flight control, travel, and hydraulics. The pilot should select the number 1 flight boost. This also turns off the number 2 flight boost. Number 2 pressure will drop to approximately 0, and the caution light will come on at 2000 psi. Depress the centering button on the cyclic control to check the full travel of the cyclic and pedals. There should be induction of motion to the rotor system. There should be approximately 6.5 inches aft cyclic and 7.5 inches forward cyclic. Be sure the controls are not binding. Check control pedals for freedom of movement, full travel, and induction of motion to the rotor system. To check the thrust control, depress the thrust control brake release trigger. Check the thrust for full travel and possible binding. Release the brake trigger and check the brake. Then return the thrust to the 3-degree detent. Next, place the hydraulic boost in the both position. At approximately 2100 psi, the caution light should go out. Select the number 2 flight boost. Number 1 will then register approximately 0, and the caution light will come on. At this time, the co-pilot should reset the master caution light and check his controls in the same manner. When these actions have been completed, the pilot must place the boost switch in the both position. At approximately 2100 psi, the caution light will go out. The pilot should now decrease the number 1 and number 2 engine beep trim switches for 8 seconds. Now, the pilot searchlight filament switch, then the co-pilot searchlight filament switch will be placed in the off position. CH-47 cockpit and engine start procedures up to main engines were covered in this presentation. Seatbelt checks, jettisonable door release handles, and other general items were described first. Then attention was given to the overhead switch and circuit breaker panels. The instrument panel was next in the cockpit procedure sequence specified by the -10, followed by the check items for the CH-47 console. We then performed the APU start sequence, the flight control and lighting check, fire detection check, fuel quantity check, and hydraulics check. Part 2 of this presentation will cover starting procedures for the CH-47C, beginning with the main engine start.
This presentation deals with reconnaissance in confined area operations, including high reconnaissance, low reconnaissance, and ground reconnaissance, pinnacle and ridgeline operations, slope operations including upslope, downslope, and cross-slope landings, external load operations, high overhead approach, and low-level approach. First, let's consider reconnaissance in confined area operations. To make an overall evaluation of an area and its surrounding terrain, first, select a good vantage position for observation. Maintain a constant airspeed of 70 to 80 knots, maintaining constant altitude. The altitude and flight path you select will be governed by the terrain and availability of forced landing areas. The altitude should be low enough to permit study of the general area, high enough to afford a reasonable chance of making a successful emergency landing, yet not so high nor so distant as to prevent adequate study of the proposed landing area. Determine the suitability of the landing area. Locate any barriers and estimate their effect on wind. Select a point for touchdown and plan the approach. Plan the best flight path for your eventual takeoff, always remembering to have your flight path over the best available emergency landing areas. Next, make your pre-landing check. You are now ready for your approach into the area. Always remember, the angle of descent should be steep enough to permit clearance of the barrier by a safe margin, but it should not exceed a steep approach angle. Complete the approach to the ground when surface conditions are favorable. Now, let's consider low reconnaissance. It begins on final approach when you are low enough to study the area in detail, and when you are able to distinguish small objects on the ground. As you approach, continue to study the immediate vicinity of the selected touchdown point. Remember, never land in an area from which a takeoff cannot be made. If, as in this case, a successful completion of the landing is in doubt, perform a go-around before loss of translational lift. Execute a flyover for further study. Determine if a landing can still be accomplished in the area. It may be necessary to re-enter a high reconnaissance to determine if another approach route and touchdown point would be more suitable for an approach. A ground reconnaissance must be performed before you maneuver the helicopter. Normally, you can make your ground reconnaissance while seated in the cockpit. Determine the suitability of the area and reconfirm all factors noted previously on your high and low reconnaissance. Now you are ready to maneuver the helicopter into position for the takeoff. Pick the aircraft up to a hover. Move to a takeoff point that you have selected. Prior to landing the helicopter on the takeoff point, perform a hover check. With the hover check completed, land the helicopter. Now, take off from the confined area. Use the amount of power necessary to clear the barrier, maintaining a constant angle of climb. Remember, clearing a barrier by a narrow margin with a reserve of power is more desirable than clearing it by a wide margin with maximum power. In a small area, a vertical takeoff may be executed. This is done by increasing thrust until the desired power setting is attained, applying cyclic and directional pedals to maintain position over the ground. Climb vertically until intercepting an angle that will clear the barriers. Apply forward cyclic to attain translational lift and continue the climb. The requirements for pinnacle and ridgeline operations are the same as for confined area operations. There is only one exception, the takeoff. In making the approach, use the normal approach angle as a standard. However, a shallow or steep approach angle may also be used. Terminate your approach well forward on the area to avoid severe turbulence. Place the wheels lightly on the ground while maintaining sufficient power to keep the aircraft light on the landing gear. As power is decreased, check to make certain the helicopter is on firm ground. Only then should you complete the landing. Remember, exercise extreme caution during touchdown on uneven or rough terrain. In a takeoff from a pinnacle or a ridgeline, always keep in mind that the takeoff point is higher than the surrounding terrain. Therefore, it is desirable that you make an airspeed over altitude takeoff. Gaining altitude on takeoff is of secondary importance to gaining a safe single-engine airspeed. A slope landing may be necessary during confined area, pinnacle, or ridgeline operations. Therefore, you as a pilot should practice landing on inclined surfaces. In this presentation, consideration will be given upslope, downslope, and cross-slope operations. Of the three, upslope operations are preferable. Let's consider upslope operations. In an approach to a slope, allowances must be made for wind, barriers, and forced landing sites. In addition, you must always be aware of turbulence and downdrafts. Prior to landing, set the parking brake. The landing will be accomplished from a hover. Lower the thrust, gently placing the forward landing gear on the ground. Apply forward cyclic as necessary, being careful not to get droop stop pounding. Lower the thrust until ground contact is made with the rear landing gear. After all landing gear are firmly on the ground, place the cyclic control in the neutral position. This should be done to ensure that there is safe head clearance on the upslope side of the helicopter. Caution should be exercised when performing upslope landings. Always be aware of the possibility of ground resonance or thrust bounce. To perform the takeoff, apply forward cyclic, increasing thrust until the aft gear break ground and a hover attitude is attained. Neutralize cyclic and continue to increase thrust until a 10-foot hover is attained. The downslope landing may be useful at times as a means of leveling the cargo compartment for easy loading. To accomplish a downslope landing, slowly lower the helicopter from a hover, gently placing the aft gear on the ground. Maintain hovering attitude with the thrust as you apply 2 inches of aft cyclic to hold the aircraft on the slope. Bring the forward gear in contact with the ground by continuing to lower the thrust. Care must be taken not to exceed the aft cyclic limitation. When all 4 gear are on the ground, lower thrust to the 3-degree detent. Then neutralize the controls. To take off from the downslope, position the cyclic 2 inches aft. Apply thrust until the aircraft is at a hover attitude once again. Maintain this attitude with the thrust as you apply forward cyclic. Continue to apply thrust until the aircraft breaks ground and is hovering at 10 feet. You may find the attitude indicator very helpful when performing slope operations. The cross-slope landing is the least desirable way to land on a slope, but in field operations, it may sometimes be a necessity. When performing cross-slope operations, the pilot must take extreme care not to exceed control limitations. Hovering parallel to the slope, lower the aircraft vertically until the upslope aft gear is on the ground. Use pedals to maintain heading. Place the forward upslope gear on the ground, using lateral cyclic to hold the aircraft on the slope. Lower thrust until the downslope gear are on the ground. After the aircraft is firmly on the ground, neutralize the controls. To perform the cross-slope takeoff, position the cyclic laterally into the slope. Apply thrust until the downslope gear comes off the ground and the aircraft is level. Apply aft cyclic to get the upslope forward gear off the ground and the aircraft to a hover attitude. Further, increase thrust, maintaining hover attitude until the upslope aft gear breaks ground and a 10-foot hover is attained. Many missions performed by Chinooks require carrying external loads. Before beginning external load operations, crew members must be briefed with regard to individual responsibilities. The cargo hook must be checked for condition and to be sure it will operate properly. Checking load rigging is the responsibility of the aircraft commander. During hookup, takeoff, and approach, the pilot who is not flying will monitor the engine instruments and torque meter and control rotor RPM. Before hookup, the cargo hook switch must be placed in the armed position. Hookup operations begin with hovering over the load. Positioning the aircraft over the load for hookup is accomplished by the flight engineer giving directions and adjustments to the pilot.
Forward 5, down 5. Hold your forward, down 2. Hold, load is hooked. Hold. Alright, wind up easy. Wind up easy. Easy. Lines are coming tight. Turn it up. Lines are coming tight. Lines are coming tight. Alright, slings tight, man's clear, bring it on up.
When the load is hooked and the hookup man is clear, hover altitude must be increased until the load clears the ground and reaches an altitude of 10 feet. A power check is next to ensure sufficient power for takeoff. Accomplish takeoff by applying forward cyclic to accelerate into translational lift, using thrust as needed to establish a simultaneous gain in airspeed and altitude. After a normal climb is established and the load is riding satisfactorily, the cargo hook switch must be placed in the off position. How well a load rides determines the airspeed at which it may be carried. On final approach, the cargo hook must be placed in the arm position. Airspeed is being dissipated toward the end of the approach, so care must be taken to maintain sufficient thrust to slow the rate of descent and halt the aircraft. The approach should be terminated at 0 airspeed with the load 10 feet above the ground. Directions from the flight engineer enables the pilot to position the load. Reduce hovering altitude until the load is on the ground and the sling is slack. Release the load on command from the flight engineer. He will confirm load release.
Load's on the ground, bring it down 5, back 5. Keep release the hook. Hook's through, you're clear to go, sir.
Remember that there are three types of sling loads: high density, low density, and aerodynamic. Each must be handled in a specific way. A high-density load, a howitzer or a sling load of ammunition, for example, may be flown up to maximum recommended speed for the aircraft, provided it rides well. A low-density load, for instance an empty Conex container, must be carried at a much slower speed. If speed is too fast, a low-density load will swing or ride up against the bottom of the aircraft. The aerodynamic load is the final type to be considered. A light fixed-wing aircraft is a good example. Such a load must be carried rather slowly, or it may begin to fly on its own, striking the transporting aircraft or moving into the rotor blades. Now, let's consider the proper procedure for making a high overhead approach. A high overhead approach is necessary when descending into an area from a high altitude in order to minimize exposure time to possible enemy fire. To perform the high overhead approach maneuver, lower the thrust to initiate a descent. Begin a turn and trim the aircraft. Maintain rotor RPM within limits. Use the airspeed, rate of descent, and amount of turn necessary to reach the desired area. Airspeed, rate of descent, and amount of turn required will vary with entry airspeed, entry altitude, and the tactical situation. So good planning and judgment are essential. The final approach into an area should resemble a normal or a steep approach. The final approach should be into the wind. The aircraft should be level, and thrust must be sufficient to slow both rate of descent and ground speed. Again, angle of descent should be steep enough for safe clearance of barriers, but should not exceed a steep approach angle. The approach should be completed to the ground when surface conditions are favorable. Like the high overhead approach, the low level approach is used to minimize your exposure time to possible enemy fire. Do not perform a low level approach over open terrain. To do so would mean possible exposure to enemy fire. When you perform a low level approach, fly at 120 knots or velocity never exceed whichever is slower. Make certain your altitude is at least 150 feet above the obstacles. Be sure and maintain this altitude until you have slowed down sufficiently to begin the final descent into the landing area. If at all possible, select a landmark on your approach path. This landmark should be at least 1/2 mile from the landing area so that you can slow down in time to complete your approach. This presentation has dealt with CH-47 advanced maneuvers and field operations, including confined area operations, pinnacle and ridgeline operations, slope operations, external load operations, high overhead approach, and low level approach. When making high reconnaissance for confined area operations, select a good vantage position for observation. Your angle of descent should not exceed a steep approach angle. Never land in an area from which a takeoff cannot be made. During takeoff, use whatever power is necessary to clear the barrier by a safe margin. In pinnacle and ridgeline operations, exercise extreme caution during touchdown on uneven or rough terrain. It is desirable that you make an airspeed over altitude takeoff. When performing slope landings, always be aware of the possibility of the ground resonance or thrust bounce. Upslope operations should always be chosen over cross-slope operations if there is an alternate. Before beginning external load operations, crew members must be briefed with regard to individual responsibilities. During hookup, takeoff, and approach, the pilot who is not flying will monitor the engine instruments and torque meter and control RPM. Positioning the aircraft over the load and placing the load on the ground is accomplished through communication between the flight engineer and the pilot. In a high overhead approach, good planning and judgment and coordination of airspeed, rate of descent, and amount of turn are essential in order to terminate at the desired point of touchdown. Never perform a low-level approach over open terrain. The landmark you select should be at least 1/2 mile from the landing area. This presentation has covered confined area operations, pinnacle and ridgeline operations, slope operations, external load operations, high overhead approach, and low-level approach. Ability to properly perform these maneuvers is essential for rotary wing aviators serving in combat areas.
The CH-47 Chinook is the workhorse of the Army's helicopters and one of the most versatile aircraft ever developed. It can carry men, it can carry cargo, and it can carry bulky sling loads like a giant skyhook. The Chinook is also an example of extremely complex engineering. Thousands of precision parts must function correctly in every successful mission. Even under the best of conditions, component failures will occasionally occur. And in combat, an emergency condition resulting from enemy fire is not at all unusual. As a Chinook pilot, you must be prepared for emergencies at all times. You must know, first of all, how to determine exactly what has gone wrong, then what to do about it before it's too late. In an aircraft as complex as the Chinook, there are a great variety of emergencies which can occur, particularly when you're flying in combat areas. This film is going to concentrate on 13 of the most common, but your operator's manual alone lists over 50. It wouldn't be a bad idea to know them all. Emergency conditions in the Chinook can be divided into two major categories: flight control emergencies and engine and powertrain emergencies. The hydraulic flight control system in the Chinook represents the primary flight controls. A loss of pressure in this system would leave you without any control whatsoever, were it not for the fact that this system, like several others in the Chinook, is a dual system designed for just such an emergency. These two identical systems share the workload during normal flight. If one fails, The other automatically takes over the entire load. Your first indication of trouble will be the illumination of the master caution light. On the caution panel below, the hydraulic pressure warning light will be on for whatever system has failed, and the second hydraulic system automatically assumes the load. Move the hydraulic boost switch on the overhead panel to the number 2 position. The flight can be continued normally, but with particular attention toward an impending failure in the remaining hydraulic system. SAS failure. In order to help you fly the Chinook without constant corrections, it is equipped with a type of autopilot system. Known as the Stability Augmentation System, or SAS, it is a dual system designed to assist in aircraft stability. A SAS failure can take 2 forms. The milder one is called oscillation. The first sign that this type of failure has taken place will be your own awareness that the aircraft has lost its stability in one of its 3 axes. The oscillating Chinook will tend to porpoise through the air in that axis, and you will have to apply constant control to override the effect. Your first corrective action should be to determine which of the SAS systems is malfunctioning. To do this, move the SAS switch to the number 1 position. This gives control entirely to the number 1 SAS system. If the oscillation continues, the problem is in the number 1 system. Place the SAS switch in the number 2 position to turn off the malfunctioning system. This should eliminate the problem. But take care to observe single SAS airspeed limitations. The more serious SAS failure is known as hard over. It causes sudden and severe attitude changes. Fortunately, this usually occurs in only one axis. Your first action should be to regain control of the aircraft. But to do this, don't fight the hard over condition. Turn off both SAS systems by moving the emergency SAS release switch to the release position. The aircraft is now under your control. Remember, hard over is a dangerous and unpredictable condition. Do not try to find out which SAS system malfunctioned. This can cause an equally severe condition known as reverse hard over. Without SAS, the Chinook is too unstable to fly for any great distance. Do not attempt it. Instead, reduce airspeed and make a landing as soon as practical. Another electrical malfunction that can affect flight controls is the failure of a generator. The Chinook has dual generators to cope with just such an emergency. However, if the second one should fail as well, you would have an extremely hazardous situation on your hands. In the case of single generator failure, your first indication will be illumination of the master caution light. On the caution panel, you'll find one of the generator lights has come on. As your first corrective action, have the co-pilot move the failed generator switch to the test position. On the master caution panel, check the warning light to see if it remains on or goes out. If the light remains illuminated, the generator has failed, and the generator switch should be placed in the off position. If the light goes out, the generator should be turned on, indicating that the failure is in the electrical circuit or an electrical component which can be located and be removed from the electrical circuit. Failure of the thrust magnetic brake is one of the many serious problems that occur during a complete electrical failure. But this system can also malfunction on its own. The magnetic brake is designed to hold the thrust control rod in whatever position you set it. You will first become aware of the failure when you find the thrust control rod frozen, making it impossible for you to move it. This can be particularly hazardous when in a descent. Electrical power to the brake should be immediately cut off by pulling the thrust brake circuit breaker on the overhead panel. This should release the brake, enabling you to move the rod. However, sometimes the brake will remain frozen. To free the thrust rod, try to slip the thrust brake by pulling the rod up. If it doesn't slip, you and the co-pilot continue pulling. The brake will shear under 45 pounds of pull. You may continue the flight normally at this point, but remember, the magnetic brake is no longer operable, and you must hold the thrust control rod at all times. Under these conditions, you can easily induce thrust bounce. Thrust bounce is a severe vertical vibration. It is usually brought about when the pilot's grip on the thrust control rod is too tight. With the magnetic brake inoperable, the inflexibility of such a grip allows the aircraft's vibration to feed back through your arm into the thrust control rod and the flight control system. This creates a dangerous cycle. If not quickly corrected, it will soon bring many components to their fail points. To eliminate the condition, try loosening your grip or changing the position of the thrust control rod momentarily. This is often enough to break the cycle of vibration, and the thrust bounce condition should subside. The possibility of a condition known as ground resonance exists in all helicopters. Related to thrust bounce, this condition occurs on landing when the main landing gear touches down. A combination of weak thrust magnetic brake and/or pilot control touch at that moment can sometimes start a severe vertical vibration of the fuselage. This may become so violent, it can destroy the helicopter. If you feel ground resonance begin, do not try to complete the landing. Immediately raise the main landing gear off the ground or bring the aircraft to a hover. Do not let the ground resonance continue. In just a few seconds, it can begin to tear the aircraft apart. When the vibration has subsided, you may try another landing. Unlike flight control emergencies, engine-related failures are often more difficult to detect in their early stages. In most cases, there are no caution lights to signal trouble, and these failures will not usually cause an immediate change in the sound of the aircraft. Unless you are alert, you can suddenly find a critical emergency condition already happening. 3 instruments are of primary importance in diagnosing engine and powertrain emergencies. These are the torque indicator, the rotor tachometer, and the N1 indicators. Scan these instruments constantly while in flight. Know how they function with each other. Know how they can be expected to behave in all kinds of emergencies. In the case of engine failure, your first sign of trouble will show up on the torque indicator. The torque needles represent the amount of torque being developed by each engine and are normally married on the indicator. As an engine failure continues, however, these needles will begin to separate, with one moving higher and the other lower. When you see this condition developing, check your rotor tachometer. If the engine is failing, you will see a loss of RPM. You should strongly suspect an engine failure, but you cannot be sure until you check the N1 indicators. Here, N1 will be falling, but only if it drops below 60% can you be sure that an engine failure has taken place. As soon as you have diagnosed the problem as engine failure, decelerate to 70 knots, the best single engine airspeed, and have the flight engineer visually check the failing engine. Then adjust the rotor RPM to 230 and move the engine condition lever to the stop position. Next, make sure that the fuel supply to that engine is shut off. At the same time, The co-pilot should monitor the EGT indicator for any sign of rising temperatures in the shutdown engine. This would indicate fire. The flight engineer should report no fire or smoke. When you are satisfied that there is no engine fire, open the cross-feed fuel valve in order to utilize your full fuel capacity to feed the remaining engine. Once you have completed engine shutdown and fire check, continue the flight, observing all the limitations of single-engine flight as described in the operator's manual. Engine fire. An engine fire can develop after, during, or before your instruments begin to show an engine failure is taking place. In most cases, your first indication of fire will be the illumination of the fire handle for the affected engine. Immediately alert the crew, and at the same time, go into a shallow descent. Do this before investigating any further. If the fire cannot be extinguished, you will have a head start toward a safe landing. Ask the flight engineer to visually confirm that number 1 engine is on fire. There is still the possibility that the fire handle has given a false signal. Move the engine condition lever to the stop position. Then decelerate to 70 knots. By this time, the fire can be confirmed. Beep up your remaining engine to normal rotor RPM. Then pull number 1 fire handle to shut off the engine's fuel supply and arm the fire bottles. Now discharge the number 1 fire bottle into the burning engine. The Chinook has only 2 fire bottles. Do not use the second fire bottle unless it is clear that the first one has failed to put out the fire. Follow up by making sure the number 1 fuel valve to the burning engine is also closed off. When you are sure that the fire has been extinguished, you may end your descent and climb back to altitude. Do not attempt to restart the shutdown engine, but in order to use full fuel capacity, open the cross-feed fuel valve. Continue the flight, observing all the limitations of single-engine flight. Low beep failure is an emergency condition that can easily be confused with an actual engine failure. You must be able to distinguish the two conditions, or you may shut down an engine because you mistakenly believe it has failed. As in engine failure, the first indication of trouble will be the separation of needles on the torque indicator, with one moving higher and one lower. Immediately check your rotor tachometer. RPM here will be dropping off to about 220. These readings so far are about the same as in engine failure. But again, the N1 indicators will provide the conclusive reading. In a low beep failure, the N1 indicator for the affected engine will be falling, but it will stabilize at or about 60%. Decelerate to 70 knots. And have the co-pilot pull the number 2 engine AC trim circuit breaker. You no longer have AC control of the affected engine. Control reverts to the emergency engine DC trim switch, located on the console. This switch must now be used to bring RPM on the engine back to 230. Caution, this must be done carefully with short flicks of this spring-loaded switch. Continue adjusting until the needles on the torque indicator are back in an overlapping position. You may then resume normal flight. If any further beep problems arise, again use the emergency DC trim switch to correct them. Fuel boost pump failure. Loss of engine power can also come about indirectly through the failure of both of the fuel tank boost pumps. This can create an emergency when you're at higher altitudes because the engine-driven pumps may be unable to supply fuel above 6,000 feet. A boost pump failure need not create a serious emergency or even result in an aborted mission. Illumination of the master caution light will be your first sign of malfunction, and the fuel pressure light shows which fuel boost system has failed. Open the cross-feed fuel valve before the engine fails from lack of fuel. This allows the fuel in the remaining tank to supply both engines. Since the left tank fuel pumps can service the engines for an indefinite period, you can consider the emergency over and continue your mission. However, if you do not act quickly enough and one engine does fail from lack of fuel, immediately decelerate to the best single-engine airspeed, 70 knots. Then open the cross-feed fuel valve and prepare to make a normal air start of the failed engine. Transmission oil pressure loss. Although it doesn't sound very dramatic, this can be the most serious emergency of all. This is because all 5 of the Chinook's complex transmissions are oil lubricated. A sufficient loss of oil will allow so much heat to develop that breakdown of the affected transmission and rapid disintegration of the aircraft is almost sure to follow. Your first sign of trouble will again be the master caution light. You'll find the transmission oil pressure light illuminated. Without checking any further, begin an immediate descent. If there is an oil loss in the transmission, there is little you can do about it, and it is important to be in a position to land as soon as possible. As you descend, check the oil pressure in each of the 5 transmission systems. This can be done with the transmission pressure selector switch on the center panel. As the selector is turned, the pressure of each transmission will register on the main transmission pressure indicator. If there's an oil pressure loss, this will identify the failing transmission. This is not conclusive. It could be a false indicator reading from the transmission. To confirm it, check the temperature of that transmission. This is done with the temperature selector switch. If the aft transmission is losing oil pressure, its temperature should be above normal and rising. You must assume that a failure in the transmission oil pressure system is taking place. Return the transmission temperature selector switch to the scan position. If the problem had been in one of the engine transmissions, marked left or right, your best solution would be to shut down the affected engine and continue with single engine flight. But since the loss is in one of the main transmissions, you have one alternative: an immediate emergency descent. You must get on the ground as quickly as possible now, because there is no way of knowing how much longer the transmission will continue to turn the rotor blades. Emergency descent is a hazardous technique to be used only under extreme conditions. Besides loss of transmission oil pressure, the only other situations usually calling for an emergency descent are a fire in a fuel tank, the hydraulic or transmission fluid system. First, inform the crew that an emergency descent is being made. They will need time to secure all cargo and strap themselves in. If a sling load is being carried, drop it immediately. Next, push the thrust control rod all the way down in order to sustain maximum rate of descent while still maintaining rotor RPM within safe limits of 261 or less. At the same time, the co-pilot should issue a mayday call. As you descend, pick out the best possible landing area within your maximum glide distance. Don't try and stretch it to a larger field farther away. You may not make it. It's possible to come down either with or without power. However, the only time a no-power, auto-rotational landing would be advisable is when the site you've selected is an area of high trees. Otherwise, it's best to land with power. You may need that extra bit of power flight capability. Once you've landed, if there's time, shut down all systems before leaving the aircraft. It may prevent additional explosions or damage. And you should learn the location of all the Chinook's 14 emergency exits. The knowledge may come in handy. The Chinook is a safe and well-designed aircraft, but normal component failure and combat damage occasionally create emergency conditions. You may never encounter any of the emergencies we have just seen, but if you are as well prepared for them as this pilot and co-pilot were, you should have no problems. Remember, if a hydraulic system loses pressure, switch to the good system. If one SAS system malfunctions and an oscillation develops, continue on the other SAS system. But if a hard over occurs, turn off both SAS systems and land where practicable. In a generator failure, test the generator for proper operation. Reset the generator or turn it off and continue the flight using the remaining generator. A frozen thrust control rod probably means magnetic brake failure. If the circuit breaker won't release it, slip or shear the brake. A tight grip on the thrust control rod can bring on thrust bounce. To stop it, you must break the cycle of vibration. If ground resonance begins, do not attempt to complete the landing. Hover till stabilized before landing again. In an engine failure, the N1 indicator will fall below 60%. In low beep failure, the N1 will hold at or above 60%. Use the emergency engine trim switch to beep the engine up. Confirm engine fire before shutting down the engine. Use one fire bottle at a time, only as necessary. In boost pump failure, open the cross-feed fuel valve immediately. If loss of transmission oil pressure is confirmed, begin an emergency descent. If carrying a sling load during an emergency descent, release it. Have the co-pilot make a mayday call and terminate if possible with power. No matter how much flying skill you develop, you cannot foresee emergencies, but you can learn how to handle them. All of the emergency procedures you have seen, and many more, are described in Chapter 4 of your operator's manual. To emphasize its importance, this is the only chapter whose pages are marked in red. Study this section. Learn all the procedures. More than that, understand why these procedures are called for. Know what to do without having to consult the manual. Expect the unexpected. The safety of your aircraft, your crew, and yourself may depend on it.
Army aviation personnel are familiar in a general way with the Chinook helicopter. Its twin-turbine engine, tandem overlapping rotor configuration, and quadricycle landing gear are distinctive features. In this film, we will examine the Chinook and become familiar with its design and its systems. The Chinook has clean lines and efficient design for its mission, the transportation of troops and cargo. Engines, transmissions, and drive shafts are located on top of the fuselage, with no obstruction of the cargo compartment. For comparison, the Chinook is 1.5 feet shorter than the Shawnee, but its cargo compartment is 10 feet longer than the Shawnee. The rear ramp and door open and close hydraulically. They are controlled by a lever at the right rear of the helicopter. Without engines operating, pressure from a hydraulic accumulator actuates the ramp. If the accumulator has insufficient stored pressure, this hand pump can be operated to increase pressure to operate the ramp as well as other hydraulic components, which we will see later. The Chinook may be flown with the ramp partially or fully open to accommodate extra long cargo. Provisions are made to carry cargo too bulky for the compartment. An 8-ton capacity cargo hook for external loads is provided. The lower rescue door is unlatched. It is opened manually with a crank which moves it down and aft to lie parallel to the fuselage when fully open. When the retainer straps are released, the hook swings down into operating position. The ends of the beam are trunnion mounted to the fuselage so that the load can sway fore and aft without inducing pitching movements in the aircraft. The hook is roller mounted on a curved beam so that side-to-side swaying of a sling load does not tend to make the helicopter roll. The load is normally released hydraulically. As an aid in the loading or unloading of cargo, a hydraulic-powered winch is provided in the front end of the cargo compartment. The winch is equipped with 150 feet of steel cable and a high and low-range gear shift. The cable can be rigged through overhead pulleys to hoist personnel or cargo through the hatchway. Moving now to the exterior of the Chinook, we will observe some of its service and maintenance features. Fuel tanks are contained in pods on each side of the aircraft. Ease of maintenance was one of the chief design considerations in the Chinook. For example, the landing gear components are readily accessible through access panels. And right and left landing gear components are interchangeable with minor modifications. All of the Chinook's access panels are hinged to the fuselage. They cannot be dropped or blown away while maintenance is being performed. For use during ground operations, 2 external interphone receptacles are provided, one near the entrance door. The other, also on the right side, is at the aft end of the aircraft. Steps are provided at the forward and aft ends of the aircraft on the right side. Work stands and ladders are not required. Platforms are built in wherever they are needed. All regular maintenance jobs can be with no-slip surfacing runs down the length of the helicopter. Parallel with the walkway is a tunnel, shown here with covers removed, through which the drive shaft to the forward transmission runs. The tunnel also carries hydraulic lines, electrical wiring, and control linkage. With these items accessible from the exterior, inspection and maintenance can be performed even with the Chinook fully loaded. There are no components requiring periodic inspection under the cargo compartment floor or within its walls. A grease gun is practically unnecessary on the Chinook. Bearings on the rotor head assembly are all oil lubricated. Each oil reservoir has a sight gauge for checking the lubricant level. The control rod ends and bell cranks are dry lubricated and require no greasing. The Chinook has been referred to as an hydraulic helicopter. Its hydraulic systems contain an unusual amount of plumbing. The Chinook has 3 completely separate hydraulic systems, referred to as Flight Control System number 1 and number 2, and the utility hydraulic system. These 3 systems are completely separate. Each has its own fluid reservoir, plumbing, and pump, driven by the accessory gearbox on the aft transmission. The 2 flight control systems do identical jobs, and the Chinook can be flown with only one of the 2 systems operating. The flight control systems provide hydraulic power to operate the stick boost actuators, the stability augmentation system extensible links, and the upper boost actuators. The stick boost actuators are situated in a lower flight control compartment just aft of the co-pilot seat. These hydraulic actuators are operated by movement of a system of push-pull rods and bell cranks which run under the floor to the cockpit flight controls. They supply hydraulic assist for the cockpit flight controls. The stability augmentation system extensible links are the muscles of the system you will hear referred to simply as the SAS. The SAS links are located just above the stick boost actuators. They automatically make corrective movements of the flight controls to compensate for minor variations in pitch, roll, and yaw. As muscles, they receive their orders from a gyroelectronic brain which senses and corrects for these minor deviations. The upper boost actuators are also referred to as pivoting and swiveling actuators. They are connected between the swash plates and the structure of the aircraft. Their extension or retraction moves the swash plate to control the flight of the helicopter. The boost actuators are controlled by valves, which are operated by rods, running to the flight control mixing unit. This unit receives thrust, pitch, roll, and yaw movements from the lower controls and converts these 4 movements into 2 integrated movements for the swash plate. These rods run aft to similar upper boost actuators on the aft swash plate. We can see that the Chinook's flight control system is completely dependent on hydraulic power. It is a fail-safe system, however, since the controls operate efficiently with only one of the 2 hydraulic systems operating. The utility hydraulic system consists of a hydraulic power and engine starting system and 5 subsystems. The ramp actuating system, the rotor brake and aft wheel swivel lock and brake system, the hoist system, the cargo hook release system, and the forward wheel brake system. All 5 subsystems are powered by one pump in the hydraulic power and engine starting system. This system is unique in Army aircraft. To describe it, we will start with the hydraulic accumulator we saw earlier. If pressure is low in the accumulator, it can be recharged with the hand pump. In a diagram, it looks like this. When a valve is opened, pressure flows to the APP motor pump. APP is the abbreviation for the auxiliary power plant, which we shall see in a moment. The APP motor pump is a dual function device. It serves as a motor to start the APP. Then, after the APP is operating, it serves as a pump to provide hydraulic pressure. Therefore, the APP motor pump drives the APP engine to start it. Then, is driven by the APP to serve as a hydraulic pump. With the APP started, pressure flows to an accessory drive motor. This motor, in turn, drives the accessory gearbox. With the accessory drive motor operating, the accessory gearbox and all of the Chinook's hydraulic and electrical systems can be operated without starting the main engine. the utility system pump, the two flight control system pumps, and the electrical system's two alternators are all driven by the accessory gearbox. With the accessory gearbox driving the utility system pump, the 5 utility subsystems are pressurized. The same pressure from the utility system pump is used in the main engine starters. These starters are hydraulic motors, which crank the engines up to starting speed. With the engines operating, power flows to the aft transmission, which then takes over the job of driving the accessory gearbox. Before we move on, let's review the hydraulic power and engine starting system. To provide hydraulic and electrical power, the accessory gearbox must operate. This can be accomplished in 2 ways. Stored hydraulic pressure in the accumulator can be used to drive the APP motor pump. Acting as a motor, it starts the APP engine. Now, the APP motor pump functions as a pump to drive the accessory drive motor, which operates the accessory gearbox. With the accessory gearbox functioning, all of the utility subsystems, as well as the flight control hydraulic system and electrical system, can be operated for ground check or maintenance. To start the main engines, the same procedure is used to obtain utility system pressure. This pressure is then diverted to the hydraulic engine starters, which start the main engines. The engines now provide hydraulic and electrical power by driving the aft transmission and accessory gearbox. The Chinook's hydraulic engine starting has one important advantage. The aircraft is truly independent in the field. External electrical power is rarely required. The Chinook's battery is small, since it is used only to provide starting ignition. The utility hydraulic system's 5 subsystems do not differ very much from similar systems found on other Army aircraft. The ramp actuating system's operation was described earlier in the film. The rotor brake, the aft wheel swivel lock, and the brake system consist of 3 separate hydraulic circuits. One circuit passes through an accumulator and rotor brake control valve to the rotor brake. Pressure stored in the accumulator assures that the rotor brake will function even with the utility system depressurized. Another hydraulic circuit runs to the swivel lock control valve and onto the left and right swivel locks. These locks retain the aft wheels in a trailing position. The third hydraulic circuit goes to the aft brake control valve and then to the left and right aft wheel brakes. The aft brakes are parking brakes. They are not maneuvering brakes and do not function when the pedals are depressed. The Chinook's forward wheel brake system does not differ from the maneuvering brakes on other aircraft. The pedals are operated conventionally and operate the front wheel brake. The hydraulic hoist system circuit includes a hydraulic motor to drive the winch and a hoist control valve to control its speed and direction. A simple circuit also operates the cargo hook release system. The hydraulic hook release valve is normally operated electrically by the pilot, co-pilot, or crew chief. In the event of malfunction of the normal system, the hook can be released manually by the crew chief or from the cockpit by blowing it open with compressed air, which is stored in a chamber inside the hook. The Chinook is the first Army helicopter with a dual alternating current electrical system. The two alternators each supply 208 volts of three-phase, 400-cycle current to two separate circuits. If one alternator fails, the other automatically supplies the entire load. For components requiring direct current, dual transformer rectifiers are situated in the forward end of the left part. A nickel-cadmium 24-volt battery is located in the same compartment. It supplies emergency DC power and starting ignition for the APT. The Chinook AC system delivers more watts of power per pound of system weight than a DC system. Let's take a moment to learn the functions of three systems which help the pilot to fly the Chinook. The Stability Augmentation System, or SAS, promotes stability by reducing the effects of turbulence. When the Chinook pitches, rolls, or yaws, the SAS immediately feeds in corrective control movements. SAS relieves the pilot from making constant minor adjustments for variations in pitch, roll, and yaw. The Differential Collective Pitch Speed Trim System, or DCT, provides a positive cyclic stick position at high rates of speed. It also corrects for the abrupt changes in speed caused by gusty winds. If flight airspeed is constant and the Chinook is temporarily displaced longitudinally by gusty winds, the system will automatically return the helicopter to its original airspeed. The longitudinal cyclic speed trim system increases the efficiency of the Chinook at high speed. Normally, when a helicopter increases its speed, it assumes a nose-low attitude. The longitudinal cyclic speed trim system overcomes this in the Chinook. When the Chinook's speed is increased, the longitudinal cyclic speed trim system tilts the rotor disc so that the fuselage remains nearly level, thereby reducing fuselage drag. In the cockpit, there is a change we should note. The control which adjusts collective pitch is called a thrust rod. To move the thrust rod, this trigger must be depressed to release a magnetic brake which normally locks the thrust rod in position. The magnetic brake can be forced or broken in the event of a jam. When making collective pitch changes, it is not necessary to simultaneously twist the grip to adjust power output. Power is automatically adjusted as collective pitch is changed. In addition to the standard instrument panel configuration, the Chinook is equipped with electrically anti-ice and defogged windshields. Electrical current passing through a conductive film between two sheets of glass keeps the windshield to remove ice or fog. The Chinook is a complex but rugged aircraft. All of its components are designed for long and trouble-free life. Let us review some of its unique systems. Its loading ramp provides easy access to the large cargo compartment, equipped with a hydraulic winch which can pull cargo into the helicopter through the ramp opening or through a hatchway in the cargo compartment floor. An 8-ton capacity hook is provided for sling load operation. Ease of servicing and maintenance were prime considerations in designing the Chinook. Work stands and ladders are not needed. All panels are hinged in place. All regular maintenance can be performed with tools from the standard mechanic's toolbox. The drive shaft, hydraulic lines, electrical cables, and control rods run through an easily accessible tunnel at the top of the aircraft. The Chinook uses hydraulic power to perform many functions. It has two complete flight control hydraulic systems which normally operate simultaneously. Either system can carry the full load, however, if the other fails. The utility hydraulic system consists of a hydraulic power and engine starting system and 5 subsystems. Dual alternators provide alternating current for most electrical equipment. Dual transformer rectifiers and a battery supply electricity to units requiring direct current. 3 electro-hydraulic systems aid the pilot by increasing stability in turbulence, compensating for gusty winds, and maintaining a level attitude at high airspeed. In the cockpit, there are a number of features which are new in Army aircraft. Every unique feature incorporated in the Chinook is designed to make it more effective in its mission, the transportation of troops and cargo. In the field, the Chinook fills an important position in the Army's progress toward air mobility. Its large payload, both in weight and bulk capacity, greatly exceeds the capability of any helicopter in its class. With the Chinook, we have come a long way toward reaching the ultimate in rotary wing design.
The effectiveness of a modern army hinges on its mobility, and mobility today means transport by air. The CH-47, the Chinook, has made a tremendous contribution to the Army's mobility in carrying men, equipment, supplies, and arms. A helicopter can get into places that a truck or fixed-wing aircraft can't. It means fast, sure delivery of materiel. And bringing men to their destination more rested than if they'd come on foot or by truck. The Chinook can carry about twice as much cargo as a 5-ton truck usually can. It can transport 3 full squads of combat-equipped troops. The Chinook has folding seats. The aircrew lowers them and secures them either before they leave their base or en route. The Chinook will be ready for you when it arrives. The Chinook has one cargo door. A crew member operates it from inside the aircraft. The door lowers to form a loading ramp. You should not approach a Chinook from the front because of the danger from the rotor blades. Come in from the rear in orderly squad formation. Troop boarding is as simple a procedure as taking a seat and strapping in. Maintain squad integrity for the flight. A crew member will check to ensure that you are properly strapped in before taking off or landing. Troop transport is important. But so is the transport of cargo. The requesting unit, your unit, must inform the aviation people beforehand what the cargo is and its weight. Prepare your vehicles for transport before the aircraft arrives. Windshields lowered, antennas tied down, gas tanks no more than 3/4 full, and center of gravity marks clearly indicated on all vehicles. An aircraft crew member will inspect for all of this. Put the vehicle in four-wheel drive to back it up the Chinook's ramp. Aircraft crew members will guide you on. On the basis of the information your unit gave, the flight engineer will have a loading plan prepared. He'll direct your vehicle to the proper spot in the aircraft so the helicopter will be properly balanced in flight. If you're loading more than one vehicle, lash the first one down before you pull the second one on board. The lashing is easier that way with more room to work. Generally, for tying down vehicles, use the MB1 tie-down device, a 9-foot chain with a rated strength of 10,000 pounds. In tying down a vehicle, first get the distance from the tie-down point in front. That's the bumper, straight down to the floor of the aircraft. Measure this length straight out in front of the vehicle, and then another 2/3 length. That gives you the straight 30-degree angle. Measure one length to the side, and you have the combination angle. Use the nearest ring farther away from the vehicle. Don't go to one closer in. If you prefer, you can go to the other side for a closed angle of tie. Remember, a 30-degree angle of tie from the floor of the aircraft up to the attachment point of the vehicle is measured one length down, 1 2/3 lengths out, and one length over. Looking down from the top, a 30-degree angle off the center line of the aircraft, this angle can go outward as here, called an open tie, or inward called a closed tie. Attach the chain to the vehicle using the L-shaped hook. Keep the hook with its loop facing upward, the open side down. Prepare the quick release hook by pushing the safety catch and turning the ratchet to extend the hook as far as it'll go. When you attach it to the floor ring, the butterfly mechanism, which is the quick release, must face upward. Pull the chain taut and place one link in the hook's chain pocket, while you ratchet the hook back in as tight as you can get it. Tension will keep the link secure in the chain pocket. Pad the chains where they cross with burlap bags, worn-out clothing, or if there's nothing else around, even several layers of cardboard. A Chinook's cargo is by no means limited to vehicles. As we said, it can transport large amounts of supplies, ammunition, or what have you. The tie-down device recommended for general cargo is the CGU-1B. This has a 20-foot nylon strap rated at 5,000 pounds. Before you can tie down general cargo, you've got to unitize it. You'll probably use the same CGU-1B devices for this. The strap has a movable hook at one end and a stationary hook at the other. It's a simple matter to hook the two together. Unitize the cargo completely so it'll behave as though it were a single piece. The recommended way to tie down general cargo is with a straight 45-degree angle. Attach the stationary hook first. To find a 45-degree angle, measure down from the top first and straight out the same distance. That's it. Again, use the nearest ring farther away from the cargo. Attach the stationary hook first, then the movable hook. You'll always need more tie-down devices running fore and aft than you will to the sides. Again, use the appropriate manual to determine the number of devices you'll need for the weight of your load. You may have a piece of cargo with a great deal of weight concentrated in a small space. The aircraft's floor won't support this weight without a load spreader. The appropriate technical manual will tell you if your cargo is heavy enough to require load spreader shoring. Each item of cargo must be placed in accordance with the load plan determined by the air support unit. To make sure of this, the aircraft commander or a crew member will recheck the weight and balance requirements before he takes off. Not all loads can go inside the Chinook's cargo compartment. The terrain at your destination may be too rugged for a landing. Or the cargo may be too heavy to manhandle on board or too big to fit inside the aircraft. An external load is the answer. If an external load flies broadside to the wind, it will spin or swing in flight, a dangerous situation for the aircraft. For stability, it's got to fly front end first. The center of gravity of the swing load is always directly under the apex. This box has the same characteristics of a swing load. Using a fan to produce wind, we can simulate forces acting on a swing load in forward flight. Because of the relatively light weight and large surface area of the box, it becomes violently unstable and uncontrollable in flight. One means of stabilizing the box is to add weight, which changes the weight-drag surface ratio. The box may become stable, but the load will still fly broadside, which will slow the aircraft down. Another means of achieving stability is by shortening the front two swing legs and adding weight to the forward area of the load. Notice the center of gravity is still under the apex, but has shifted to the front portion of the load, and the load will now fly with the smallest surface into the wind and with a high degree of stability. Rigging a howitzer is basically like rigging any other sling load. You must use the proper equipment and follow proper procedures. Slings should be inspected before and after each use. Check for the presence of all cotton buffers in the loop ends of the slings. Check the sliding keeper and the fixed keepers. The month and year that an air delivery sling is placed into service must be stamped in 1-inch lettering near the first keeper on both ends of the sling. Check for evidence of broken or loose stitches, fraying, excessive wear, fuzzing, nylon burning, or cuts in the nylon webbing. Common damages to air delivery slings are nylon burning and sling cutting. Nylon burning or fusing is caused by friction and the resulting heat that occurs when nylon comes in contact with other nylon or metal surfaces. The lifting ring is formed by using two 3-foot slings and Type 4 link assemblies. Make sure the locking button on the link assembly is in place. Position the link assemblies on the side so they will not come in contact with the cargo hook. Check the lifting rings as you would any other sling. Nylon burning of the slings can be prevented by padding the slings where they come in contact with metal surfaces or other sling segments. Light padding is usually sufficient to prevent friction. In rigging the 105mm howitzer M101A1 with piggyback load, ammunition is included as part of the load. First, the choker hits the 8-foot sling around the tube over the padded area. Place your sling to the rear of the breech. For the ammunition load, choker hits one 11-foot sling around each trail over the 1-inch padding forward of the traveling lock shaft. Pull the sling through and align it on the padded area. Ensure the cotton buffer is in place to prevent nylon-to-nylon contact. Drop the sling through the trails. The same procedure is used on the other side. It is essential the slings are placed in the proper location. Otherwise, the load will be improperly rigged, and there is a chance of damage to the aircraft and the load. The aft legs are rigged by attaching one 11-foot sling around each trail in the area of the padding aft of the traveling lock shaft. Here again, ensure the cotton buffer is in place to prevent nylon-to-nylon contact, which could cause the sling to break. Join the 3 lifting slings with a large clevis. It is important that the 8-foot sling is in the center of the clevis with the 2 11-foot slings on each side. Attach the other 8-foot sling to the bolt of the large clevis assembly. Tighten the bolt. At the other end of the 8-foot sling are the 2 3-foot slings used to form the lifting ring. Snug up all keepers. To join the ammunition load to the howitzer, attach the 11-foot slings that are forward of the traveling lock shafts to the lifting slings of the cargo bags with clevises. By interlocking the clevises, the piggyback load will remain attached to the howitzer in case one of the slings breaks, and it offers more stability to the load in flight. Police the landing zone thoroughly. This applies to all helicopter operations. Pick up all loose debris. If you've rigged the load correctly, everything will go as it should. The hookup crew stays until all slack is taken up and the piggyback load is off the ground. Then the hookup men move away to the aircraft's right. In all of its many roles, the CH-47 Chinook has more than earned its stripes. Whether carrying troops or hardware, the Chinook offers dependable and fast transportation. The offer is there. Its fulfillment is up to you. Every mission depends on you on proper load operations. Learn the loading procedures and follow them to the letter. The CH-47 Chinook will take care of the rest.